In lesson 6.4, we're introducing this topic of logarithms. And I'm going to use the next slide as a way to introduce this concept and hopefully make a connection to something that you did long ago. Probably back in elementary school you did exercises like this when you were first introduced to the idea of exponents. The terminology that you were taught, this number that sits below the exponent we call the base, and then of course this is the power or the exponent. And in this little exercise you would be asked to put the exponent that would be required to make this a true statement and write that number in the box. So for example, you would say, well, obviously that has to be 2 to the second power, or the missing exponent would be 2. Here the missing exponent would be 3. Here the missing exponent also 3. And then over here, the idea of negative exponents you probably didn't cover in elementary school, but here we need negative exponents because 2 to the 4th would be 16, but 2 to the negative 4 makes the reciprocal of 16, which is 1 over. This would obviously be negative 2, and this would be negative 3. Well, the reason why I went through that little simple exercise is because when we think about logarithms, we essentially are doing pretty much what we just did in this little exercise. A logarithm, by definition, and you need to write this in your notes, it's the power to which a fixed number called the base, we identified the base, here the base is 2, base is 3, 5, and so forth. A logarithm is the power to which a fixed number, which is the base, must be raised to produce a given number. So we basically ran through some pretty simple examples of exponents that are required to make a base number, a given base number, a fixed number, equal or produce a given number. And in other words, we found the missing exponent. So that's really what logarithms are. If you ever answered the question, what is a logarithm, by saying it's an exponent, you would be correct, because essentially logarithms are exponents. Now they're not just any exponent, it's the required exponent needed to make a true statement like we have here. There's only one exponent that could be used for a base of 2 to make it equal 1/16, and that's the exponent negative 4. So I wanted to use this as a way to work our way to the definition of a logarithm. And now let's take a look at some examples of really what we're going to be doing in this exercise. Not a real complex exercise at all, but a very important one for what we're going to be doing in subsequent lessons starting tomorrow and then on throughout the week. So we're familiar with this blue exponential form, some base raised to an exponent indicated here by y equals another number. We just looked at some of those. Well, now I want to introduce you to what we call logarithmic form, or we just shorten that and we'll say log form. Notice how we can take an exponential equation and turn it into a log equation. Well, there's some things to notice. First of all, this number labeled as b, which we call the base of the exponent, is the same number that we use for the base of the log. Alright, this indicates that it's really the same number. If this were 2, then this would be log base 2. Alright, another thing to keep in mind is going back to our simple definition of what logarithms are. Essentially, logarithms are exponents. So the exponent in this exponential form is y in this case. Well, notice how I let the log equal the exponent because, again, that's what logarithms are. In other words, you could read this as the log is the exponent that we're seeing in this exponential form. And then that just leaves this other number in the equation. So let's just take a look at some examples using regular numbers. Here's a true statement in exponential form. 3 to the second is 9. Here's that same statement using log form. Log, and here's how it reads. Log base 3, notice the base of the exponent, log base 3 of 9 is 2. Logarithms always equal exponents. Since the exponent in my exponential form is 2, then I'm going to let the log equal 2. So a couple of things to take note of here. I on purpose drew this line that represents your ruled notebook paper. You have the blue lines probably on your notebook paper. Notice how I wrote everything on the line except for the base, and the base drops below. We call this subscript. Okay, so I'm trying to get you to think about a particular format, and I use this illustration in class. Sometimes people just get careless and they just start running away with stuff, not thinking that it really matters. This does not mean 3 to the 9th power. Okay, obviously that can't be the case because we're trying to reproduce an equivalent expression for 3 to the 2nd power. Well, 3 to the 2nd power is completely different from 3 to the 9th power. So this does not read as 3 to the 9th. It reads as log base 3 of 9 is 2. So when you're writing log equations, just keep in mind, write everything on the line except for the base, and you can drop it below. Alright, same thing here. Exponential form, a true statement is 5 to the 3rd power is 125. Well, here's that same exponential statement written in log form. Log base 5 of 125 is 3. Okay, so now that you've seen some examples of exponential to log, and eventually we'll be going in the other direction, we'll be taking log form and writing exponential. Let's do some examples like your homework problems. So these are some illustrations, some examples of problems 13 to 18 in your assignment. Given these log equations, let's write the related exponential equation. Alright, so remember the base of the log is 2, so that means the base for an exponent has to be 2. Logarithms are exponents, so I'm looking at an exponent of 3. Logarithms are exponents, so that means the base of 2 is going to be raised to the 3rd power, and that has to equal 8. Alright, and that's true. So again, we're just taking one form and we're writing in an equivalent form, a different form, but it still means the same thing. Okay, that's my answer for letter A. Letter B will be a base of 8 raised to the 2nd power is equal to 64. Letter C, 49 raised to the 1/2 power is equal to 7. Letter D, 4 base raised to the -3 power is 1 over 64. Letter E, a base of 8 raised to the 3rd power is 512. Letter F, 5 raised to the 4th power is 625. Letter G, 3 raised to the -2 is 1/9. Now I put a little star by H because as you can tell, it's different than the rest. I'm not showing a base number. There is a base, but it's not showing. So I wanted to give you a heads up. Whenever you see this going forward, this will be true whatever math class you take. If there is no base written or showing or printed in your book, it's always understood to be base 10. This is called the common log. And the reason why 10 is the only base like this that's understood if it's not showing is because we have a base 10 number system. And so if I'm taking letter H and I'm writing it in exponential form, I would say 10 to the 2nd power is equal to 100. Alright, and so those are all log equations that have been converted into exponential or form equations. Alright, well now let's go the other way. Let's take these exponential equations and we'll see if we can write them in log form. Alright, so we're going to need the word log, short for logarithm. Base of 7 for the exponent, so that means the base of the log will also be 7. Log base 7 of 49 is equal to the exponent 2. Logarithms always equal exponents. Here we have a base of 10, so I'm not going to write base 10. If you did, I wouldn't mark it wrong, but that's the one base that doesn't need to be written. Log base 10 of 1/10 equals the exponent -1. Here, log base 8 of 64 is equal to 2. Log base 6 of 1 over 36 is equal to -2. Log base 4 of 64 equals 3. Here we have a base of 11. Log base 11 of 1331 equals 3. Here the base is 16. The exponent is 3/4. Log base 16 of 8 is equal to the exponent 3/4. And here we have log base 17 of 1 equals the exponent 0. So we've converted the other way. We took exponential equations and we wrote them as log equations. Okay, and then finally, the last part of your assignment will involve this little exercise, and your instructions simply say to evaluate each expression. Well, the root word of evaluate is value, and when we talk about a value in math class, we're basically talking about a number. Evaluate is another way of saying come up with the number. Well, when we're talking about evaluating log expressions, it's not just any number. It's, well, let's just put it in quotes here. Evaluating a log expression means to find the missing, or you might think required, exponent. Remember, a logarithm is an exponent. I can't say that enough. So evaluating a log expression means find the necessary or the required or the missing exponent. To do this, I want you to show your work in this way. I want you, and here's my little green note, I want you to change given log expressions into exponential form first. Okay, just take that little step that's going to take you maybe a few seconds. So what I'm about to do on these, you will follow this same pattern when you do 25 through 36. Alright, so here I have a log expression, log base 2 of 8. Here is that same expression using an exponential form. For now, I'm just going to say that the exponent is unknown. I'm going to call it x. So 2 to some power is equal to 8. Well, that power, that's now is where I'm going to evaluate the expression. I'm going to determine what this required exponent is. And to finish off my answer, I'm going to say it's 3. Okay, letter B, I want you to take this given log expression and write it into an exponential equation. 81 as a base raised to some power is equal to 9. When you evaluate a log, you are finding the missing or the required exponent. And in this case, that exponent would be 1/2. 81 to the 1/2 is the same thing as the square root of 81. Okay, letter C, I want you to turn it into 5 raised to some power is equal to 125, and then tell me what that power is, or evaluate the log. That would be 3. Letter D, in exponential form, we would say 1/7 raised to a power is equal to 343. And what is that power? That power would have to be -3. Letter E, I want you to show it as 13 raised to something equals 169. So evaluating this log means find out what this required exponent is, and in this case it would be 2. Letter F, 2 to some power is equal to 1 over 128. And maybe take a little bit of work with your calculator, but that should be -7. 2 to the 6th is 64. 2 to the 7th is 128, but if we want the reciprocal of 128, we have to use a negative exponent. Now letter G is interesting because in exponential form it says 5 raised to some power is equal to negative 25, and we had a little discussion about this in class. And here's the bottom line. There is no way to raise 5 to a power and make it equal negative 25. So anytime you're asked to evaluate the log of a negative number like this, you're going to say that either it's not possible or it's undefined. Since we're not given an equation in the book, I'm not going to say no solution, because a solution involves finding the answer to an equation. And I know we're creating an equation for practice, but just because they didn't give me an equation to solve, I'm not going to put no solution. But if you put not possible, that would be okay. So I just want to bottom line this for you. Your bases will always be numbers greater than 1. They will not be negative. So therefore, it's impossible to evaluate the log, no matter what the base is, of a negative number. So be on the lookout for those cases. Here, I would say this is 64 raised to some power is equal to 2. And we said earlier, using common bases, 64 is 2 to the 6th. And remember this little common base technique. If you let the exponents equal each other, now that we have common bases, you can solve the exponents. We did this a few days ago. So my answer here would be 1/6. Okay, so I think I gave you enough examples to help you. There's plenty of examples there, but this is such an important skill. It's very foundational for the next couple of lessons. So work real hard on that, and let me know if you have any questions.